Here's a beautiful geometry problem. A triangle with side lengths 13, 15 and 17 is inscribed inside a circle. Your challenge is to find the radius of the circle. But there's a catch. We are only going to use triangle rules, Pythagoras theorem and circle theorem. Pause the video now and see if you can solve it before we begin. Take a few seconds. Look carefully. The key idea is hidden in the diagram. Let the triangle be ABC, where AB equal 13, BC equal 17 and AC equal 15. Let's start by drawing the altitude AD from the top vertex A to the base BC. This creates two right triangles, triangle ADB and triangle ADC. We'll first determine the height AD. Let BD equal x. Then DC equals 17 minus x. Applying Pythagoras to triangle ABD, AD squared plus x squared equals 13 squared. So, AD squared equals 169 minus x squared. Applying Pythagoras to triangle ACD gives AD squared plus 17 minus x all squared equals 15 squared. AD squared equals 225 minus 17 minus x all squared. From equations 1 and 2. So, we have found BD. BD is approximately 6.85 units. Now, let's find AD using Pythagoras again. AD squared equals 13 squared minus BD squared. So, the height of the triangle is approximately 11.05 units. Now comes the key observation. Point E is the center of the circle. The line AF passes through the center. That means AF is the diameter. And this completely changed the problem. According to Thales' theorem, any angle subtended by a diameter is a right angle. Therefore, angle ACF equals 90 degrees. Notice that angle ADB is also 90 degrees. This suggests that triangles ABD and AFC may be similar. Let's verify. Angle ADB equals angle ACF. Both are 90 degrees. Also, angle ABD equals angle AFC because they subtend the same chord AC. Therefore, triangles ABD and AFC are similar. Using similar triangles, AD corresponds to AC and AB corresponds to AF. Therefore, AD over AB equals AC over AF. Substituting the known values. Therefore, AF is approximately 17.647 units. So, we have found the diameter. Since AF is the diameter, the radius is simply half of AF. Therefore, the radius of the circle is approximately 8.82 units. What makes this problem beautiful is that the difficult looking circle disappears once we identify the hidden diameter. The entire solution relies on three classic ideas: Pythagoras Theorem, Thales Theorem, and similar triangles. A great example of how one observation can transform a geometry problem. Did you spot the diameter before the solution? Let me know in the comments. And if you enjoy the geometry puzzles like this, don't forget to like, subscribe and share. See you in the next challenge.